Good morning. So today we switch the subject. So we postpone the quantum mechanics for a while and start considering some combinatorics of surfaces. And namely, we will consider the algebraic object, which is known as a mapping class group of a surface. And we will consider a special class of surfaces which are known as the puncture surfaces. Mapping class group. Okay, mapping class groups of puncture surfaces. So we will consider the an oriented surface of finite type. Finite type. So sigma, which is will be written with two indices, sigma gs, and this will be the same as a closure of sigma minus finitely many points. So, which that means that the genus G, S points removed. For example, this is a sigma 2, 3. And we assume that there is at least one puncture, and the second that its Euler characteristic is negative, which means that 2g minus 2 plus s is positive. So this is these conditions can be thought as conditions of the fact that the surface admits a constant curvature metric with the curvature negative. But we can think of those conditions in more simpler terms. Namely, these are exactly the conditions which admit the existence of ideal triangulations. So these conditions imply that sigma admits ideal triangulations. So this is a key phrase in here, ideal triangulations, and that means that it's a CW decomposition of sigma bar. So the closure, we add back the punctures. So it is closed oriented surface of genus G. But it is not arbitrary CW decomposition, but a decomposition where the vertex set is given by punctures, is P1, PS, and all two cells are triangles, and all two cells are triangles. So let's see examples. So let us start with a minimal case of type 0,3. So we cannot have less than 3 punctures in the case of sphere, because when G equal to 0, so we need at least 3 S to have this inequality. And indeed, we can imagine a cellular decomposition of the sphere of the following form. So we put 3 points on the equator, then the upper hemisphere and lower hemisphere are topological triangles. Right? So this is a same thing as just one triangle in the plane. Here I identify S2 with R2 with point at infinity. So the plane of the blackboard is R2, so we have a point at infinity. Then in the finite part, we have one triangle, and the complementary region is another triangle. Okay, which is, if we think in the perspective of 3-dimensional space, then we have just a round sphere, but 2 halves of it, two cells.
Excuse me,
which are triangles.
Is that second condition correct? Because 2G minus 3 plus S greater than 0 is trivial if G is greater than or equal to 0.
Trivial what?
S is larger than 0 and G is larger than or equal to 0. So.
What's the problem with this?
It seems trivial.
No, it is not trivial if G is less than, if G equals 0.
Sure.
Right? Because if G is at least 1, then it is trivial. Okay. But if G equals 0, which I'm discussing, so S should be at least 3. So we can't have S equal 1, which is okay with here, but not okay with here. Okay? But of course, this is not the only possibility for that type. So we keep the same type, but we can imagine another triangulation, which is a round sphere. But this time I put on the north and south pole punctures, and then I draw again the equator and put just one puncture on the equator. And then I can imagine, so this is an edge, this is an edge, and the equator is an edge. And this is also a triangulation. So if we draw in the plane, then what we see, we see 3 points in the finite part, and one circle like this. And probably it is not evident that we see triangles as 2 cells, but they are. They are because this guy is a triangle, because we can think of it as a result of gluing, self-gluing of a triangle like this. But from the viewpoint of cellular complexes, that's okay, because the interior of the cell should be embedded. While on the boundary, we can have self-identifications. Okay, so this is sigma 0, 3. Let us see sigma 0, 4. So we have one more puncture on the sphere, and we can think of, for example, the boundary of a tetrahedron. And the natural cellular decomposition into edges and triangles. So in the sequel, I will also draw tetrahedra in a two-dimensional picture, just identifying R2 with a complement of a point in S2. And in this case, we can think of a Mercedes sign, which is a triangle put, which is a tetrahedron put in the plane. So the one face is the outer face on the plane. And finally, and of course we can have many more possibilities, as maybe not many, but there are other triangulations. And let us see the genus 1. So genus 1 with one puncture. Then, so in three-dimensional perspective, we draw a torus, and we want to decompose it into triangular cells. So we pick up a base point. That's a puncture. And then we cut open along, we draw a non-contractible loop like this. We draw a non-contractible like this. And we know that the complementary region for this wedge of two circles is a rectangle. And we can split this rectangle into two triangles by adding a diagonal. And adding a diagonal means that we draw something like this. And we can draw it just a plain rectangle with opposite sides identified and with a diagonal added. And we have 4 copies of the single puncture on the surface. So if we glue the torus, then these 4 vertices are identified to one single vertex. Okay, so, but this picture is different from those because the outer region doesn't exist in this case. Okay, so that's the ideal triangulation. And now we refine this notion by defining a decorated ideal triangulation. So the definition, decorated ideal triangulation is an ideal triangulation where all triangles are linearly ordered, and a distinguished corner is specified in each triangle. So let me draw an example. So we take sigma 0, 4. So we have a tetrahedron. That's an ideal triangulation. But we now linearly order. So which means that we enumerate the triangles. So we say this is the first triangle, for example. This is the second, this is the third, this is the fourth. That's a linear order. And then we have to specify a distinguished corner in each triangle. So we put a dot near the distinguished corner. For example, here, here, and here. We have 3 choices for each triangle. And here. That's a decorated ideal triangulation. And now we define a set, delta sigma. This will be the set of isotopy classes of decorated ideal triangulations. So isotopy class means that we can move continuously the cells. But essentially, the cellular structure is given by drawing the edges. So we can deform the edges. Like this is the same as okay, let me. This is the same as this. And this is isotopy. So I have deformed this vertical edge. Like this. Okay, so no questions? Okay, this set is delta sub sigma. And I define another object, which is called MCG of sigma. So the mapping class group. Second key notion of today's lecture, after this delta sigma, mapping class group, which is a MCG of sigma. And what is this? This is effectively the set of all homeomorphisms which preserve the orientation of sigma, quotient with respect to the normal subgroup of the connected component of the identity. So this is topological group with a compact open topology. And in this topological group, we have a set of connected components. And effectively, mapping class group is as a set is this set of connected components of the space of all homeomorphisms. But this set carries the group structure inherited from the composition of homeomorphisms, because the connected component of the identity, this concerns any topological space, is a normal subgroup. Connected component of identity sigma. Okay, and then the important remark is that MCG of sigma freely acts on delta sigma. Everybody knows what is a free action of a group? Good. Okay, so I'm not going to prove this, but I'd like just to remark that without decoration, this statement is not true. But actually, to make the action free, we don't need too much of decoration. One can show that it suffices to fix an orientation on one single edge of an ideal triangulation to make the mapping class group action free. But for some reasons, we don't want to stay with a distinguished edge, which is a kind of global thing, right? Among all edges, we have to distinguish one. We prefer to put more decoration, but we spoil the symmetry locally. So we choose locally inside each triangle one corner, and we enumerate the triangle, but this is not a big deal. It's clear that if we accept the fact that fixing orientation on one single edge makes the mapping class group action free, then our decoration surely makes this action still free, because we can associate to our decoration an orientation on a distinguished edge. For example, we choose a distinguished edge, the edge of triangle 1, which is opposite to its distinguished corner. And we choose its orientation the way that it goes counterclockwise with respect to the orientation of the triangle 1. So it's clear that our decoration is more than enough to make this action free. And why we are paying so much attention to the freeness of this action? Because it's a very general fact that as soon as we have a group freely acting on a set, then we can construct an algebraic object which is a connected groupoid. And as an algebraic object, this groupoid will contain the complete information about our group. And our interest will be about this connected groupoid, which we will, namely in the case of mapping class group action freely acting on delta sigma. But to define this groupoid, we don't need too much details about the group and the set where it acts. So we define it on the general context of any group freely acting on any set. Okay, so let G be a group freely acting on a set X. Then define a connected groupoid denoted calligraphic G with sub-indices G, comma X as follows. So what is a groupoid? Everybody knows what is a groupoid. It's a category where all morphisms are invertible. Okay, so to specify this groupoid, we have to say what is a set of objects, what is a set of morphisms, when morphisms are composable, and when they are composable, what is their product. So we start by the set of objects. Objects of this groupoid are given by just G orbits in our set. Second, so set of morphisms of Gx, which by definition will be identified with a groupoid itself. Right? We think of groupoids as groups. But what is a group? It is just a set of elements. Likewise, in a groupoid, we think of a set of morphisms. But set of morphisms, in the extended sense, contain the full information about also the objects. Because, for example, as a subset of identity morphisms. So this is why we can remove this, the indication of morphism and just say that the groupoid itself. But anyway, what is this? So as a set, it is a G orbits in the Cartesian square of the set X. And here we have to specify that this set of orbits is obtained with respect to diagonal action. With respect to diagonal action. Okay, so we have specified objects morphisms, and now it remains to say when two morphisms are composable and what is their product. So we say that so X, Y will denote, so notation. We put X in square brackets to indicate the orbit of X. So this is Gx. And X, Y will be G orbit of pair XY. Okay, and then, so this is a notation. And we say that X, Y is composable, or XY and UV are composable if and only if the orbit of Y is equal to the orbit of U. And in that case, the product XY with the UV, it is the same thing as XY GU GV, because we are talking about orbits in the Cartesian square, so we can act simultaneously by any element of the group. And the freeness of the action is used at this moment, so we choose G in a unique way that, that GU is equal to Y. X, Y. Okay, so if G, U equal Y, then this is the same as X, Y, Y, GV. And at this moment, so the composition rule tells us that we just forget about the middle pair of Y's. So by definition, the X, comma, GV. So here, G is a unique element. Of G. Okay, which okay, let me put here. If the action is not free, this uniqueness doesn't apply. Okay, so that's our group point. And remark, or maybe remarks. So first remark, the GXG is connected. Connected, it means that for any pair of objects, the set of morphisms between them is not empty. And it is clear that you pick up two orbits of x and y, then you just take the orbit of their pair, which connects them. So the connectedness is just evident. And second thing, the set of morphisms between x and x is isomorphic to our group G. To our group G. Why we have this? And namely, we sent Hx to G to set of morphisms between x and x by the formula H sub x of G is given by x, comma, Gx and the orbit. Okay, I left an exercise to check that it's an isomorphism of groups. Yeah, and now the important theorem. It's a long theorem. I mean, not the proof, but we will not prove it. The statement is long. So the groupoid G of MCG of sigma, comma, delta sigma. So we have this groupoid now defined along this line. Admits the following presentation. So when I say presentation, I mean presentation like in the theory of groups. So to give a presentation, we have to say what are the generators, and we have to say what are the relations. So the generators. So the first set of generators is given by a couple of integers in parentheses. And this is going to be an element of our groupoid, so which means that we have to specify two decorated ideal triangulations put together, right, according to this. So here is a pair. So we have a decorated ideal triangulation, so all triangles are enumerated. And I draw here just a fragment of that triangulated surface, where I indicate explicitly the triangle with index I and the triangle with index j. Something like this. And we are talking about orbit under diagonal action. And yeah, I keep the same triangulation. But the only difference between the two, that the I and j are exchanged. So here we have j, here we have I. Okay, so we specify just pair of ideal triangulation. And the only difference between them is in the exchange of two indices, I and j, in the enumeration. So that I can put here. So there are many more triangles which triangulate the whole surface. And, but of course, this notation is not fully informative notation, right? Implicitly, we hide here the information about the choice of the combinatorial type of the triangulation and so on and so forth. But there will be no confusion if we keep this shorthand notation just indicating the essential part of the morphism. Okay, this is the first set of generators. Second set is change of corner. So it will be rho I. So I specify a triangle with index I, which carries a marked corner. And then I change the triangulation by rotating the marked corner in a counterclockwise way. And the orbit of mapping class group orbit of that pair will be denoted rho I. Again, so this notation is a compact notation where we retain only information about the index of the triangle and not more than that. And the third set of generators is, again, a set of generators indexed by two indices, so which is omega ij. Omega ij. So this is something dealt with quadrilaterals in the surface. So we draw a quadrilateral, which means there are two triangles sharing one common edge, at least one common edge. And we put the marked corners this way and put indices this way. So this is one ideal triangulation. And then we change that ideal triangulation just inside this quadrilateral. And namely, so the mnemonic rule of changing, you have to just rotate the diagonal continuously counterclockwise, keeping intact all the decoration. So the result will be this. Okay, that's the set of generators. And now, next, the set of relations. So there is 6 types of relations. So the first relation is the most evident one, maybe. Ij is equal to its inverse. Yeah, I didn't say here, but it's clear that the identity of x is x the orbit. So and also the inverse of xy is equal yx. So ij is a order 2 element. No, sorry. We are in the groupoid, so ij is not composable with itself. So we talk about different ij's, right? Even if we compose ij with itself, it doesn't mean that these are the same morphisms because of this notation. Because here we skip the information about the source and target. So you have to pay attention to that fact. Okay, so even if we have a notation I, comma j in the parentheses, it doesn't mean that we have many different morphisms denoted by this same symbol. Okay, and the context should be used to distinguish between them. And maybe coming back to here, I should make a remark that I use here a non-standard convention for composition. So we use the convention where the composition is like in pi 1 of a topological space. Okay, so we compose like the paths in a topological space, which is opposite to convention for composition of maps. Okay, so that's you have to pay to that. It's always a headache in keeping this in mind, but that's life. Okay, so this is the first type of relations. And the second type of, for the moment we are describing just the permutation group action. Then we have Artin defining relations in the permutation group. Ij, jk, ij is equal jk, ij, jk. So these two correspond the relations in the symmetric group. Next, the generator rho I. So if we compose rho I with itself, then it is the same as an inverse of rho I. This is also evident because if you do 3 times the change of corner, you are back to the original, so it's identity. Fourth type of relation concerns omega. So maybe we postpone this for after break. Okay. We continue the list. The fourth type of relations concerns the generator omega ij. So if we put omega ij composed with omega jk, then it's the same as omega jk omega ik omega ij. We will come back to this relation later on, but let me just finish with other relations. So there is a fifth relation which mixes up all three generators. And it is the following: rho ij, rho j, omega j I, rho I inverse omega ij. This is equal to permutation ij. We will come back to this relation as well. And the sixth type, they are put together under the name of trivial relations. Trivial relations include, for example, rho I commutes with rho j. Right, so if we change the corner in I's triangle, followed by the change of corner in J's triangle, we can achieve the same result by changing first in the J's triangle, followed by the change in I's triangle. This I call trivial relation. And we have also rho I omega jk, which is the same as omega jk rho I if j not equal I not equal k. Right, so if we have a triangle which is not one of the triangles involved in the omega ij morphism, then we can perform omega ij and change of corner in different orders with the same result. And also we have some, if we make rho I composed with ij, then it is the same as ij composed with rho j. Right, if we make a change of corner in I's triangle, and then we exchange I with j, that would be the same as we first exchange I and j and make the change of j's triangle. And we can continue this list likewise. Okay, so that's a theorem. That's a theorem. And let me just make a remark that how the proof goes. The proof is based on a CW complex having objects of the triangulate of our groupoid as vertices and generators as edges. No, and with comma. So having objects as vertices, generators as edges, and relations as two cells. And then the proof the proof is reduced to proving that complex is simply connected. Okay, so this is a kind of geometrical proof with that the line of reasoning. But if you are interested in a precise proof, then you can look at the description of the course. I put a reference by somebody called Kim, who has described this, a Korean mathematician. But in Penner's book also, but he deals with a little bit different groupoid. His decorations are different. But the proof adapted to his context is contained in his book also. Okay, let us now just see why this theorem, why we should believe in this theorem. Just looking that the relations make sense. So, verification of relation 4. So we draw a pentagon and we split it into 3 triangles. And so the relation tells us that the morphism omega ij should make sense, right? So that means that we have to put the decoration not arbitrarily, but the way that omega ij makes sense, which means that we have to put I like this and j like this. Then this quadrilateral exactly one part of the definition of omega ij. But if we look at this equality, so we have to verify this equality. So we start either from the left-hand side, which starts with omega ij, or we start with omega jk, which means that omega jk should be meaningful as well in our picture. And that fixes uniquely the decoration in the remaining triangle. So to make omega jk meaningful, we have to put decoration like this. Okay, so that's a starting fragment of the triangulated surface. And then we put another copy of this pentagon. And now I follow, say, the left-hand side. Then I apply omega ij. So I put here omega ij, but I put omega ij between 2 pictures, which means that this omega ij corresponds to this pair of triangulations. Remember that our morphisms are given by pairs of triangulations, right? The diagonal orbit, mapping class group orbit of pairs of triangulation. And just in this picture, I will put a corresponding label of the morphism between 2 pictures, which means that it is given by that pair in that order. And I can put also an arrow to say that this kind of morphism. But this has nothing to do with a map. So just a notation. OK, so that's omega ij. So then I should just change the interior part of that quadrilateral, keeping triangle K intact. So we copy the triangle K, and then here we change. Remember, we have to rotate continuously the diagonal anti-clockwise. So was it this? But check the definition. It should be exactly this. But I will just follow this rule. Rotation anti-clockwise. I will have this. And now we see that omega jk makes sense for the obtained pentagon. So we can rotate this diagonal anti-clockwise to end up. So we keep intact the triangle with label I, and rotate the diagonal in the remaining part. So with the result K and J. So that's the composition corresponding to the left-hand side of the equality 4. And now we follow the right-hand side. So we start from the same initial pentagon. So we put label omega jk, and this time we deal with that diagonal. So I copy the pentagon. I keep intact the ice triangle and rotate the diagonal here. So the result will be like this with J here and K here. Then we observe that omega ik makes sense in the obtained pentagon. So we put omega ik. We draw the pentagon. We keep the J's triangle intact. Rotate the diagonal. The result is this. Sorry. Something is wrong here. Yeah, because I changed the ice triangle. Yeah, now it's okay. And finally, we can do omega ij. And so it's easy to see that we end up with the same triangle. So we have closed the loop. Okay, so let me split this blackboard like this and address the relation 5. Relation 5. So we have two indices, ij, so we have two triangles. And now we have to carefully choose the decorations. So let me just put like I and J. And now the decorations should be such that the result of application rho I and rho J should be such that omega Ji makes sense. So that means that I would say that it should be here and here. Let us try this. If we try this, what we get? We apply rho I, rho J. So we change simultaneously the corners of both triangles. Counterclockwise, so we get here, and we get here. And now we apply omega Ji, right? So we have to turn our head if we want to compare with the definition. But anyway, the process of is the same, rotation of the diagonal anticlockwise. So we get to here. And now we should apply inverse of rho I. So we should move the marked corner clockwise in I's triangle. we get to here. And we remark that we are exactly in a position to be able to apply the move omega ij. We rotate the diagonal counterclockwise to get to here. And now we finish the left-hand side, and we can see that the initial configuration and the final configuration are distinguished exactly just by the exchange of I and j. Okay, so these are the most non-trivial relations, so we have verified that they make sense. And now the theorem tells us that it is enough to impose only those relations to be able to describe our group point. So that means that any other relation is a consequence of those. And this theorem allows us to introduce an algebraic notion, which will allow finally to construct representations of that group point, and in particular representations of the mapping class group, because it makes a part of that group point. So the definition, let C be symmetric monoidal category. Don't be afraid, because we will be dealing with a very concrete thing. So a basic algebraic system BAS in C is given by an object V in C and morphisms R in an endomorphism of V, R and W endomorphisms in V tensor V. Okay, so maybe here I should say with tensor product, yeah, C with tensor product denoted as usually, and symmetry denoted by PXY, family of morphisms indexed by pair of objects. Sorry for the mess. Okay, morphisms such that. So the idea of this definition is to use the previous theorem, and you will see. So such that I will write relations which mimic the relations we had in the theorem. So first of all, R should be order 3. So that means that R will be playing the role of rho I at some moment. Second, W should verify the pentagon, which is W12, W23 equal W23, W13, W12. So this is in V tensor cube. And I should say also that W12, by definition, is a W tensor identity in V. So those indices just say how W is included in the endomorphism monoid of V. So W23 is identity V tensor W, and less trivial is a W13. W13 is a W12 conjugated with P23. And P23 is the identity in V tensor PV, comma V. Okay, so everything is defined precisely in terms of the category, and this indexation just shorthand notation for some compositions like this. Okay, so that's the second property. And third property is a relation which mixes up all, and it is encoded in relation 5 in the theorem. So R1, R2, W21, R1 inverse, W12 equal P12. And this is in V tensor 2. So that's a basic algebraic system. Okay, theorem.
So here R1, R2 is something like R tensor identity.
Yes. So this is in V tensor 1, so Rx just in one copy of V. So R1 is R tensor identity V. R2 is identity in V tensor R. W12 just W, and W21 is a P12 W P12 inverse, but inverse is the same as P because it is symmetric. So P VV equal P VV inverse. And what else? Yeah, and the P12, of course, just is PVV. Theorem. Let VRW be a basic algebraic system in C. Then there exists a canonical representation F of our groupoid MCG sigma, comma, delta sigma into automorphism group of V tensor power the number of triangles, and the number of triangles is what is it? 4 2g minus 2 plus s. It will be an exercise to check that this is a number of triangles in a triangulation. Number of triangles. Sigma. Such that rho I, okay, so ij is sent to pij, rho I is sent to ri, and omega ij is sent to wij. So the sub-indexation here is similar to the indexation over there, but we have as many indices as a number of triangles. And so if we accept the previous theorem, then the proof of that theorem is very easy. We just check the defining relations. But this is not a big deal because we have defined our basic algebraic system to make this theorem true. But we gain something because this is the problem of finding. Of course, it's a problem of finding such object. But if we manage to find such object by solving finitely many equations, after all, then we gain a lot. We gain a representation of the mapping class group of any surface. And essentially, so the Teichmüller theory will allow us to construct a solution for that system eventually. Okay, so now let us see example, how it works. Example, so we take a torus with one puncture. And we can think of sigma as a real plane quotient by integer lattice. Obtained by the action. Action Mn acting on xy is given by x plus m, y plus m. Translations. And in that case, mapping class group of sigma is isomorphic to the group SL to Z, where SL to Z acts just in R2 linearly. Linearly, so we and it is generated by matrix T, which is 1, 1, 1, 0, and matrix S, which is 0, 1, minus 1, 0. So it is a known fact that any SL2Z matrix can be written as a word in letters S and T. Do you know this fact, that SL2Z is generated by those two matrices? Everybody knows? Okay.
Sorry, can I ask a question?
Yes.
And like we have one puncture on this torus. It doesn't really. I mean, SL2Z is mapping class group of a torus with all points. I mean, but one puncture doesn't change.
Doesn't change because it stays. It is a vertex in the lattice, so the vertex is sent to vertex. So so the puncture is sent to puncture. Yeah, so the mapping class group of the puncture torus is isomorphic to the mapping class group of just the torus. So now we want to, this is a general fact. Now we want to put this into our context. So for that, we have to choose an ideal triangulation first. So we want to identify this SL2Z group with a automorphism group of a given object in the context of decorated ideal triangulations. And we have to pick up one ideal triangulation as a reference one. So let us do this. Fix tau in delta sigma.
Excuse me, could you push the left board up?
Left board up, this one? Yeah.
Thank you.
You're welcome. Fix tau as follows. So we have a fundamental domain given by the vertices. In the integer lattice. And let me look in my notes to, yeah. One. So that's our reference decorated ideal triangulation. And we want to realize the generating elements of the mapping class group as the elements of our group point. So what we do? We apply, we draw the image of tau in our plane. So what we do for that, we have to pick up our matrix and act on the vertices. So 0, 0 is not moved. So let us see 1, 0. So I have to transpose this in order to be able to act by matrix. So this will be 1, 0, 0. OK, so it is not moved. And 1, 1, 0, 1, 0, 1. So it is 1, 1. And finally 1, 1, 0, 1, 1, 1 is a 2, 1. So this is tau. So T of tau, what is it? So bottom side stays intact, but the upper side is moved by one period. Like this. So this is 1, 1, 2, 1. And we keep the decoration intact, so just like this. But remember that we are in the R2 mod integer lattice. So we can choose any fundamental domain we want. right? So this is the same as if we take an original fundamental domain. So but we instead of considering this triangle, we consider its translate and forget about this triangle. So this is equivalent to that. Okay, so still we keep 1, 0, 1, 0, 1. Okay, so that's the result of applying the generator T. And now we want to make the same result without generating morphisms in the groupoid. And you can see that the pair tau T tau is nothing else but omega 1, 2. Right? You pick up this and pair it with this. You put this result here next to each other, and you just see visually that this is an omega 1, 2 element. And now the consequence, so the f of T is given by W12 in an automorphism group of V 10 to the power 2, because the number of triangles is 2. So we have a this realization of the first generator in this representation. And now let us take S generator. So S of tau is the rotated 0, 0 here, 1, 0 here, minus 0, minus 1, 1, minus 1. And we have to just rotate it clockwise, clockwise. 2, 1. Okay, you do the same, right? You act, but with the S matrix this way, and just redraw the image of the tau. And now what we see, so this is the S of tau, and on the other hand, we have the following. So we start with our original triangulation. This is tau, which is we apply twice R rho, namely the inverses. So what we get is this 1 inverse, so clockwise. We rotate it clockwise. We get to here, and we apply the inverse of omega 1, 2. We get to here. Right, but of course, this is the same as the same picture, or 0, 0, 0, 1, 1, 0, 0, 1, 1, 1. just translational image of that triangle over there, right? And then we proceed here purely combinatorially by using our generating elements. And as you see, we arrive to the same thing. So that means that tau, comma S of tau as an element of our groupoid is given by rho 1 inverse, rho 2 inverse, omega 1, 2 inverse, sorry, here inverse. Here we are. And as a result, f of S is given by R1 inverse, R2 inverse, W12 inverse. And now you can ask a natural question, how about relations for S and T? They are not free elements. They have to satisfy relations. How we see that these relations follow from our basic algebraic system. And this is nice exercise to try. For example, naturally we can try to multiply see the image of S times T. F of ST, which is the f of S by definition, f of T. So I don't erase completely this blackboard to leave f of T here. So what we have is R1 minus 1, R2 minus 1, W12 inverse W12. So we simplify. And on the other hand, we know that ST power 3 is 1. But we know that our elements are of order 3. So taking a cube of that, we get as well the identity. So this demonstrates a case where one of the relations is verified. And likewise, you can check that S power 4 is 1, which is less trivial, and you have to use all the relations now of the basic algebraic system to come to the conclusion that this relation is satisfied in the image as well. Okay, so we stop here, and the next time we will. So the rest of the course effectively is the story of construction of solutions for the basic algebraic system. And the classical Teichmüller theory will be a case of a basic algebraic system in the context of category of sets and with Cartesian product as a monoidal product, while the quantum Teichmüller theory will be another realization, a projective realization of the same basic algebraic system in the context of Hilbert spaces. And here our knowledge of Hilbert spaces will be used. Okay, so I stop. Thank you.